And now let's talk about the memory consumption of this approach. Since whenever we develop an application or write a program, the memory is one of the most important factors. And we should answer the following question: how much memory is available to sort the ID, or how much is reserved for sorting the IDs? And in my case, let's say that 64 bits are available. This is the size of simple long-dated data type, and to store the generated ID that consists of the 3 factors times your ID and 6 ID, we should distribute the bits so that we get the unique ID. And to do so, I have distributed the bits in the following way. For time, I reserved 47 bits. Since time takes the largest value and it ensures uniqueness across time, it for sure plays maybe the most important role in generating ID, because it ensures that the logic or the program or application performs, executes correctly over time. And that's why for time I reserved 47 bits, and for server ID I reserved 7 bits, and for seconds ID 9 bits. And let me explain what all these distributions mean. Let's start. Let's talk about the server ID. Server ID takes 7 bits. It means that at any time, at any given time, you can deploy up to 127 servers. 128. It means, at any given time, you can have up to 128 servers, and these are the IDs, etc. Because as soon as you deploy more than 127, it will lead to overflow. It means as soon as it reaches 128, it will take more than 7 bits, and it will actually break this distribution of bits. And that's why you can have only 128 bits. And for sequence ID, I reserved 9 bits. It means that the max value that can be assigned for sequence ID is 512 or 511 actually. And what does it mean? Let's say that time is x, and this is our server. At the same time, at any given millisecond, let's say, we can serve a lot of requests. Let's say that if we serve for example 100 requests, that's okay. This is our server with ID 0, and that's okay. 1, 2, 3, etc. These are request IDs. Well, this is totally okay, because sequence ID is 112, and it means the generated IDs will be x plus 0 plus 1, 2, up to the last request ID. But what happens when we serve more than 512 requests? Let's say that at the same time we are serving 550 requests. In this case, the first 512 requests will be assigned requests IDs from 0 up to 511. In some they give 512 IDs, and if we assign more than for example more than extra ID, it will actually lead overflow to a bit of to memory overflow, and in this case similarly it will break this bit distribution or memory distribution. It will break our logic, and that's why this is inappropriate, this is unacceptable. And to what we do is that for any request that more whose order or sequence is more than 112 to 512, the IDs are the sequence ID is reset actually, but all the remaining 38 requests will wait for another millisecond to pass so that the sequence ID is reset. Their IDs will be as following. This was X for the first 512 requests. This is this is a bit cumbersome as it's going, but it's very important to understand. See, then these 38 remaining requests will wait for another millisecond to pass, and time becomes x plus 1 compared to the first requests, and sequence ID is reset, and they can be assigned IDs as before. I mean, from starting from 0 up to 512. This is continuous all the time, and this ensures that the sequence ID never overflows. And this is how the memory distribution is constructed, or maybe I express it in the wrong way. And actually, this how memory is distributed for this approach. And next, let's talk about, or let's jump into the implementation details of this approach. This is the implementation details of the approach we discussed in Kotlin. Let's go through each line, and next we'll execute to see what is generated. First of all, we have the pod ID, that is assigned at the runtime or deployment time, and this is by default 0. And the next, we have the pod ID bits, and this is the number of bits we assign for pods. Similar is sequence bits, the number of bits we assign for sequence IDs. And next we just calculate their actual values. The max pod ID and max sequence, they are 100. They are these values here, 127 and 512 for zero ID and sequence ID accordingly. Next we have last time stamp to compare this time, and we have sequence ID. This is the sequence ID that is added to each ID. And next we have epoch. Epoch is used to calculate how much time actually passed since the start of the application, and this value stands for the January 1st, 2024, because the current system time always returns the amount of time that elapsed since January 1st, 1970. Since we don't care about this time, we are not using those values, and that's why we can use this time, this epoch, as the starting point, because this will reduce the value that is used to generate the ID. And here there's just checking that the pod ID must be in the range, and this is the actual the main function that is used to generate ID. Let's go through. First of all, we get the current timestamp. If the current timestamp is less than the last timestamp, that means somebody changed the last timestamp, and we should throw the error because this is unacceptable. And this block is the most important because and this block also is wrapped inside the lock to prevent race condition when multiple requests execute at the same time. First, we check time. If time is the same as the last timestamp, it means multiple requests are executing at the same time, and we increment here the sequence ID. If sequence ID is 0 and timestamp is equal, it means that the sequence ID reached its limit, and that's why we have to wait for another millisecond. If this is not the case, we just set the sequence ID to 0 and we are good to go. And here we are updating last timestamp, and that's it. And this is how we actually generate the ID. The combination of three factors. The first is time. Next, we shift left the number of pod ID bits plus sequence bits, and we just add this value, and this is pod ID plus not plus shift left sequence bits, and we add sequence ID. Actually, this is the basic bitwise operations, and I can just demonstrate how it works. Maybe I will be wrong, but it will be just to give insight how it's working in this hood. For this, the size is 63, right? The 63 bits is available to store the generated ID. Oh, sorry. Well, timestamp has 47 bits. Time has 47. And we need shifting bits to ensure that the bits are on their correct order or position. Time is the first to be calculated. And next, we calculate server ID, and next sequence ID. And to ensure that the time is the number of bits is on the correct order, we should ensure that these bits come after 47 bits, and that's why we shift the number of bits toward left. And this ensures that we have at the beginning 47 bits for time, and next we have for server ID the number of bits. This is 7, and next the number of bits for sequence ID, server and sequence. And this layout of the bits ensure that the ID being calculated is correct. And these are just helper functions. This just returns the current time, and this just waits for another millisecond to pass so that the sequence can be reset. And let's run the program and see what is being generated. The end generated ID is this value, and the main question was how since time always go forward, we at some point we reach the overflow, and how much time or for how many years this algorithm works. And to do so, let's calculate the number of seconds in a year, let's say I did the following calculation. That's so simple: 6 seconds in a minute, 60 minutes in an hour, 24 hours in a day, calculated by the number of years, by the number of days in a year. This is the amount of seconds in a year. And since all the calculation, time calculation is in milliseconds, I just multiply by 1,000 to convert these seconds into milliseconds per year. And this is max time value for max time value that is assigned here. Our time has 47 bits, and this will return the value 1 shifted left 47 bits. And let's see what happens. And our program can this program can be used or can function properly for 4,462 years. And this is the end of this tutorial. We have discussed a lot of things, and what I wanted to note is, first of all, I have a question for you. And how many requests can be handled per second? This is one of my questions. Please let me know if you answer the question. And to be honest, this is pretty hard from one side to understand. But if you're not limited in memory, just use UID. But if you are limited in memory, or you need numeric values, you can use this algorithm. And this is the end of this tutorial. If you liked it, please like and subscribe, and see you in the next tutorials.